Hi, this is Robert Owen. Welcome back to part 7 of my series introducing DCC digital command and control and how to implement it using the Arduino Uno. In part 6, I explained the hardware for the LN298N board and how it differed from the R3 motor shield, which in previous videos I'd shown how to implement DCC. In part 7, I want to explain how the software is set up, how I've implemented software on the Uno so that we can use the LN298N to implement DCC on our track. So the script for the R3 motor shield needs very few changes to modify it for the 298. So there's some changes to video 4. Most of it, apart from one slide, is changed. So there's very few changes. It's very straightforward. To recap on 298 and what needs to be done. If we want to get a DCC digital signal out of the top connector A, we need plus or minus 10 volts, and the width of the signal needs to vary between 100 microseconds or 57 microseconds, depending on whether you want to transmit a digital 0 or a digital 1. And to transmit 0 1s from connector A, we need to input into these two pins here either logical 0s or logical 1s with the correct pulse width of 100 microseconds or 57 microseconds, depending on whether you want 0 or 1s DCC signals. The setup for the C++ script for Uno for 298 is the same. We are saying pin 12 we will now call PIN 12, and we're saying pin 11 we'll now call PIN 11. There's a constant byte with two values in it, 100 microseconds and 57 microseconds, which we'll use to specify whether we want the DCC digital signal output to be either a digital 0 or a digital 1. And now we're setting up a data packet, a structure called a packet, which will contain the DCC packet for the train, which will consist of the 8-bit address, the 8-bit command telling the train to move forward or backwards or to turn the lights on or off or whatever, and an 8-bit XOR byte at the end, which is the error check to tell the decoder, to let the decoder calculate if the packet transmitted by the Uno has been corrupted on the way to the decoder and needs to be discarded if this XOR value is different. So the value of the train packet, I've used a standard value for the train address of 3, digital 11. For the command, I put 01, telling the decoder this is a speed byte. I put 1 in the 3rd bit, telling the train to move forward, or 0 if it was to move backwards. But obviously, 1 or 0 moving the train forward or backwards depends on which direction your train is facing on the track to start with. And the speed of the engine, I put a 0 as 4 1s, which is quite fast. The error check, the XOR, I've hand calculated it, but I needn't have hand calculated it because very shortly in this script I've implemented software to calculate the XOR or the error check directly, but to start with I've calculated this. Now in the setup I need to establish the program and set up the 298. So on the Uno I've specified pins 11 and pins 12 as output pins. So they're transmitting output data from the Uno. In some other application, totally different from DCC, I could have specified these as input pins receiving data from some circuit. And to start with, I'm putting pin 11 as digital low 0 volts, and I'm specifying pin 12 as digital high as plus 5 volts as a start. The next thing I'm doing for the train packet, I'm calculating the exclusive OR. For that last or third byte, here I'm calculating what the value of the error check is. And this function I'll explain shortly. The next thing I do, I actually transmit 100 idle packets onto the track. The first thing I do in communicating with the decoder is to send to the decoder 100 idle packets. And each of these idle packets is approximately 2.5 milliseconds long, and these 100 idle packets are used to initialize the decoder to tell it that it's probably about to receive a command packet. Now I've initialized the decoder, the script goes into a constant loop. I'm sending a packet called go straight, which transmits from the Uno via the 298 to the train the command packet. Then I'm transmitting 2 idle packets, because according to DCC specs, there needs to be at least a 5 millisecond delay between train command packets if you're not to overload the decoder. And an idle packet is about 2.5 milliseconds long, so by sending 2 idle packets, we're implementing approximately just over a 5 millisecond gap between command packets. Here we calculate the exclusive OR of the function XOR bracket, which you saw in the script setup. And for the address byte, each of the bits in the address byte and each of the bits in the command byte, I'm going through each bit in turn from bits I0 to I7, calculating their exclusive OR and putting the resulting value into the XOR byte, which is transmitted last, the error check byte. So this function here automatically calculates the error check byte at the end by the Uno before it's sent to the 298 and transmitted to the decoder. Here now is where is the script that calculates the value to send digital zeros and ones onto the track in DCC form. This is the only part of the code from video 4 which I've needed to change to implement 298 software. And void output bit is the sub-function where I transmit either a DCC logical 0 or a DCC logical 1, and I get whether it's a 0 or 1 by looking at the bit value, and the bit value from a previous input is either 100 microseconds for a 0 or 52nd microseconds for a logical 1. First of all, onto the track, into pins 11 and 12 of the 298, I put pin 11 at high and pin 12 at low. Then I wait 100 microseconds if I want to transmit a DCC digital 0, or 57 microseconds if I want to transmit a DCC digital 1. Then I reverse these values. I put pin 11 at low and pin 12 at high from the Uno. Then I wait again 100 microseconds for DCC digital 0, or 57 microseconds for DCC digital 0, digital 1 or logical 1. These are the only changes in video 4. Now I need to implement the go straight function, which I mentioned earlier. I pick up the train packet, which consists of the address byte, the command byte, and the exclusive OR error check byte. First of all, though, I send out a 12-bit preamble, which is all ones. I send out 12 ones, followed by a 0, which is a preamble. Then I send out the 8 bits of the address byte. So I go through each of the bits in turn from 0 to 7 in the address byte, sending out DCC logical 0s or 1s. Then I go to the instruction bytes from bits 0 to 7. I go through the train command bit by bit, sending out either DCC logical 0s or 1s, followed by an output bit 0 to tell the decoder that the command byte is finished. I'm now moving on to the XOR byte or the error check byte. And this piece of code here sends out the exclusive OR or error check byte before transmitting at the very end of the packet a bit 1 to signify to the DCC decoder on the engine that this is the end of the command byte, and what will follow now will be some idle packets before the next command byte comes along. I mentioned before in earlier videos the control packet is a set of 12 ones followed by a 0 bit to signify the end of the preamble. Then I send out the address byte. In my situation, I'm using 3, which is the default value for all decoders, which is digital 1 1. Then a digital 0 to mark the end of the address byte, and what's coming next is the command byte, followed by digital 0, followed by the error check byte, followed by digital 1, which tells the decoder that the control packet has come to an end, and what's going to follow now are idle packets. The idle packet has a different format. The preamble is the same, 12 ones followed by a 0. The address, unlike the train control packet, is 8 ones, all ones, followed by a 0. The command is all zeros, 8 zeros, followed by a 0, and the error check is calculated to be all ones. At the end of the idle packet, we transmit a digital 1 in DCC to signify the end of the idle packet. Now, this is the idle packet. I won't go into this because it was explained in video 4. The structure of the idle packet and the normal packet was explained in video 2 as well, the structure of it, the software in video 4. I won't go through this again, but it's identical to video 4. Okay, so thank you for listening to part 7 on implementing the 298 software on Uno, and in the next video, part 8, I'll explain how I've implemented an engine simulator on a board to save me setting up my model track every time I want to run software. And I'll show you a video of this code working on a real train. Thank you.